So section 5.5 is going to talk about vectors. And what I want to start out with is a discussion of parallel vectors. Now this used to bother me, and I'm not sure if I've gotten used to it or it just doesn't bother me anymore, but I'm going to change my display to be a little bit bolder by clicking the tool icon and then clicking that letter A, the capital letter A. But what I've got here is the vector at 2, -1. So that's a directed line segment from the origin to that point. So it's got magnitude and direction, making it a vector. Now, a parallel vector is anything that points in the same direction. So if we take the slider and move it to the right a little bit, you can start to see a little tracer come out, and you get an orange vector that's pointing in the same direction. Might not be the same length, but it's pointing in the same direction as vector 2, -1. Now, I can go past this like this, or I can go a little bit short of it, or I can just equal it. Doesn't matter. But what does matter, what I want to get across is that these are all parallel vectors. No matter where I move this cursor, these vectors are parallel. They point in the same direction. Now, the part that used to bother me is this. If instead of using a positive value for this letter A here, what if I used a negative value? According to definition, these are still parallel. They're pointing in the same direction. I'm a little uneasy with that. If you are too, then you're like me. But that's the definition of parallel we're going to be working with. So now, remind me what a unit vector is. Can anyone tell me what a unit vector is? No?
1 over the length of the vector?
Okay, so yeah, that's how you create a unit vector is you take your vector and divide it by its length. So perfect. And a unit vector is going to have a magnitude of what? How about maybe 1 unit, right? So if I click this little circle here for unit vector, I can see that anything with a unit vector would have to lie in this circle. And in particular, right now I've got the unit vector that points in the same direction as the vector 2, -1. So they have the same direction, but different magnitudes. By the way, what's the magnitude of this vector? Can anyone figure that out real quick? What's the magnitude of 2, -1? Square root of 5. Well done. So this is the square root of 2 squared plus -1 squared, which is square root of 5. Nice. Unit vector is going to have a magnitude of 1. And you can see that there's a couple places where the unit vector would be right here at 1, 0, 0, 1, -1, 0, 0, -1. All those are going to be a distance of 1 away from the origin. Yay. Now, sometimes you want to create a unit, create a vector of a particular length that points in this a particular direction. So our direction, our vector had a magnitude of length 5. You could take a vector like this, a unit vector, and scale it. I said length 5, I should have said length square root of 5. You can take this vector and scale it so that it has whatever length you want. So you multiply it by the length that you need to get a vector that points in this direction and has a particular magnitude. Let's look at some of the problems that you might find in the homework. For instance, it says, find a vector of magnitude 60 that is parallel to 8i minus 6j. So the first thing that I would do is I would find the magnitude of 8i minus 6j. Well, let me write that equivalently as 8 - 6. I like it that way a little bit more than I like it this way, but they're the same thing. Now, the magnitude of that is simply going to be the square root of 8 squared plus -6 squared, square root of 100, or 10. So if I want a unit vector from this vector, I can say, all right, well, I'll take 1/10 of 8 - 6. and you write that as 8 over 10, negative 6 over 10, or you can write that in lowest terms as 4/5 and negative 3/5. That's a unit vector. If I now take that unit vector and multiply it by my desired length, so the magnitude that I want was 60. So if I want a vector that points in this direction with a magnitude of 60, I can just multiply this times this. So 60 times 4/5, negative 3/5. That's going to be what, 48 and negative 36. That's my vector. That's what I'm looking for. Something with a magnitude of 60 and points in the same direction. So all that you've effectively done is you took your unit vector and you scaled it. So equivalently to this example, we started out with a unit vector and then we multiplied it by the desired length to scale it. So we stretched it. Let's just double check that that actually works. We should be able to take 48 squared plus negative 36 squared, add them up, take the square root, and come up with 60. So square root, come on, one more time. There you go. 48 squared plus, and you got to be careful with this to put your negative 36 in parentheses and then square it. Bam, 60 as advertised. How are we looking on that first one? Doing okay here? Now, a problem that you're going to run into quite often in this section is something like this, where you're asked to find a decomposition of a vector or projection of V onto W. And let me explain what that's going to be visually. And I'm going to use another, I know, shocker, Desmos example. So let me put the link in the chat for you. If you want to follow along, you don't have to. It's not something we're going to necessarily use for our calculations. But we're going to decompose a vector V into two parts. A part that's parallel to W and a part that's perpendicular to W. So let's see. Here's vector W. Here's vector V. I want to decompose V into two parts. A part that's parallel to W. And remember, parallel just means it points in the same direction. Maybe not necessarily the same length, but it points in the same direction. And a point that's perpendicular to W. So, okay. Now, how are we going to do that? Well, we're going to take the component of V that lies in the W direction and just draw a little perpendicular line all the way down to W. So something like this. Yay. And that's projecting V onto W. So that's going to be our vector V1, and I'll highlight that in black right there. So that's V1. And I'm going to get rid of this projection part here, and we'll just keep the black part, which is V1. We're going to decompose V, which is our red vector, into those two new parts. V gets decomposed into V1 and V2. V1 is there in black. Let me get rid of the projection part. There we go. And now I need another part of V that's perpendicular to this. So, okay, let's figure out what that's going to be. So perpendicular to this line would be this line. And I want to decompose part of V onto this line. So I want to project V onto this part right here. So again, you're drawing a perpendicular line down to here. And that little piece there between the origin and this black dot, that's going to be our second vector, V2. And I'll put that in black, and I'll shut off the projection, which is in green. So the two pieces in black, right here and here, that's what we're looking for. we decompose this red vector into two parts, a part that was parallel to vector W and a part that was perpendicular to vector W. And that's it. Visually, that's what it is. Now, if you're not relating to what it is visually, okay, sorry about that. Please feel free to follow up with some more questions or comments here. Be glad to help you out. If not, then we can actually work with the mechanics. Now, you should have a copy of this in your in D2L or in the chat, so you can print this formula off if you like. If you're allowed to have a cheat sheet, then this would be one that I'd put on the cheat sheet. So vector V1 is just a scaled version of W. You're taking this scalar, V dot W divided by the length of W squared, and multiplying it by W. And then V2 is just obtained by subtraction. It's V minus V1. So let's put that into action with this particular problem. So I want to decompose vector V equals 7i plus j into vectors V1 and V2, where V1 is parallel to W and V2 is perpendicular to W. All right, so let's copy down this formula again, or at least look at this formula for ourselves. V1 equals V dot W divided by the length of W squared times W. All right, so that's going to be our V1. Let's do some calculations. Now for my vectors V and W, kind of like the last one, I'm going to write this as 7, 1 and -4, -1. I just like it in that format better. Let's see about trying to find, first of all, the dot product. Hopefully you're pretty good at the dot product. That's going to be 7 times -4, which is -28, plus 1 times -1, which is -1, over the length of W squared. So the length of W is going to be the square root of -4 squared plus -1 squared. And I need to square that. So squaring the square root is going to cancel it out. So I'll end up with -29 over 17. And actually all I've calculated right now has been just this part. I still got to multiply this times W. So let's set about doing that. I want to take -29 over 17 times this. So -4, -1. And that's going to be, let's see, what, 116 over 17 and 29 over 17. So that is V1. I'll pause here for a second. We okay with V1? Basically, you can consider this a scalar. I've seen it called alpha before. And it's just alpha times W. You're just stretching or contracting this vector to be parallel to W. So something which is parallel is just going to be a scalar multiple of W, which is what this is. Let's find V2. V2 is going to equal V minus V1. Now V1 is this right here, 116 over 117, or excuse me, over 17, and 29 over 17. For V, let's go back up here. I'm going to write V this way. I'll write this as 17 over 17. 17 over 17 reduces to 1. Well, why would I write it as 17 over 17? Anyone see the wisdom in doing that? So let's take a look here. Going back up to vector v, I wrote the 17 over 17 as a version of 1. That way, when I subtract, I've already got common denominators. 7, you can think of it as 7 over 1. If I want that to have a denominator of 17, then I can multiply both the numerator and denominator of this by 17 and get 17 over, it's going to be 119 over 117. So let's put that here, 119 over 17. And now that I've got common denominators, I can subtract. 119 minus 116 is going to be 3 over 17 and negative 12 over 17. So yay, that's my vector v2. Whew. All right, so what we'll do is we'll do another one like that, and I'm going to go back and use the example that I illustrated, but questions on what we've got here so far?
So our final answer is V2. We were searching for V2 or whatever.
Yeah, we're actually searching for both V1 and V2. So
oh, okay.
Here was V1, and that's V2.
Thank you.
Yeah.
So I think something I was messing up on was I was thinking it was foiling, but like it's only combining like terms. So like the I only can go with I and J can only go with J.
Right.
Okay.
Now, remember that these two things are perpendicular to each other. So what happens when I take the dot product of two things that are perpendicular? Do you remember? Does anyone pick that up? Chance for bonus points here. What's the dot product of two things?
Zero.
Was that Kirsten?
Yeah, that was me.
Excellent. Thank you. Yeah, let me find your name here on my list. Put a little star there for you. Yeah, but they're perpendicular. And if they're perpendicular, their dot product is going to be equal to, fill in the blank, 0. There we go. Oops. That's the wrong name, sorry. There we go. All right, got you. So if you actually do take them, multiply these things together, and the denominators are going to be the same, so I'll just work with the numerators. The dot product is going to be 116 times 3, which is going to be 348, plus 29 times negative 12 times negative 12. Probably should put parentheses around that just for looks. I get exactly 0, which I should. If the dot product of two things is 0, then they're perpendicular. And that's what I wanted, is two perpendicular vectors. Okay, let's try that again with some friendlier numbers. I guess the reason I wanted to do the one I chose is because some of the problems in the book just don't work out to be nice numbers. And I didn't want to just give you the easy ones and let you do the hard ones for yourself. All right, so let's shut that off, So here's my two vectors. So V is going to be 1, negative 3, and W is going to be 4, negative 1. All right, so let's write those down. I want to try and find two vectors, V1 and V2. So V1 is just going to be some alpha times W, because they're going to be parallel. It's just going to be a stretched version of W. And how do you calculate alpha? Alpha is going to be the dot product of these two divided by the length of W squared. So let's work on both of those. So the dot product here in the numerator is going to be 1 times 4 plus -3 times -1. The length of W squared is going to be 4 squared plus -1 squared. And then I want the square root of it. Well, what happens when you square a square root? What do those two operations do to each other?
They cancel out and just leave the
Cancel out.
number.
Cancel out, just leave the number. Exactly. So what I'll end up with is 7 over 17. So that's telling me how long I want to stretch the vector W to get the projection of V onto W. So V1 is going to be this times W. It's going to be 7 over 17 times 4 -1. Okay. Well, let's see. That's going to be 28 over 17 and -7 over 17. That's the point that I want to point to get vector V1. Now let's see that visually. Visually speaking, what did we just accomplish? Well, we figured out the point along this vector. That's the projection of V onto W. It says, all right, let's just find the portion of V that lies in this direction. So you project down. We calculated that point, and that point leads us to a vector, which is, how come this isn't showing up? Oh. What's going wrong with vector V1? Well, you can see that I've got the same thing going here. What's going wrong with vector V1? Okay, so there you go. There's our vector V1. It's just that little piece of vector W. Now let me shut off the projection part. I guess it makes a difference as to which one you turn on and off first. So shut that off, turn that on, turn that on. Huh, okay. Well, vector V1 is just this little piece underneath vector W. It's not showing up so good on this one. I don't know why. Now we need to figure out the other part, the part that's perpendicular to this. In fact, let me just shut off vector W at this point. That's our vector V1. The rest of this is going to be the projection onto something perpendicular. So I want to take and project this down over here to get something perpendicular, like that. And that'll be vector V2, which is this part. So you've decomposed this vector into those two parts. Let's find that second part. The second part is here. V2 equals W minus V1. W was 4 -1 minus 28 over 17, comma -7 over 17. Like the last one, I need friendlier numbers, or at least numbers with the same denominator. So this is going to be 68 over 17 minus 17 over 17. We'll subtract off V1 from there. When I subtract here, I end up with 40 over 17. And minus
17
becomes a plus, right?
Oh,
So there'd be minus 10 over 17.
Quick question.
I think I might have made a mistake someplace.
Isn't it
For,
V
for,
minus V1?
yeah, I thought it was going to be a V minus
Oh.
V1.
V minus V1. I was looking at this going, wait a minute, something's wrong here. All right, thank you. V minus V1. All right, so that's a bummer. V minus V1. What I was doing in my mind to say, to double check it, is that V1 and V2 should be perpendicular. And I was doing the little dot product between these and going, wait a minute, that's not going to be 0. So yeah, I appreciate you catching me on that. So V minus V1, 1, -3, minus V1, which was 28 over 17, and -7 over 17. Same trick as before. Write that as 17 over 17 minus 51 over 17. And I guess I need a new pen. So that's going to be -11 and -44 over 17. -11 over 17, and you're adding 7 there, so it'll be -44 over 17.
how many of these types of questions would you guess is going to be on the test?
Oh, no more than 8.
Huh?
So no more than 8. LOL. No, just 1. Okay, so that's that last part there. It's the projection of V2. It's going to be V onto V2. So comments or thoughts on that one? Is there a part of that calculation that maybe I went through too fast? I know I screwed up at one point, my bad. All right.